Hello everyone, welcome to the fifth lecture of the course Statistical Thermodynamics. The topic of this lecture is a review of classical thermodynamics, specifically the first law of thermodynamics. In the last lecture, we have seen that heat is nothing more than just kinetic energy. The reason it does not appear as visible motion of an object is that this type of kinetic energy is associated with the random motion of the atoms that the object is made up of. The average velocity of all the particles is zero, and so there is no observable motion. The average of the squared velocity of the particles is not zero, and that is in fact a measure of the degree of hotness of an object or its temperature. When kinetic energy is converted to heat during an inelastic collision or due to friction, the sum of the kinetic energies of all the atoms of the system is perfectly conserved, although on the macroscopic scale it may appear that kinetic energy is lost. With this background, let us now formalize an idea which is universal and has a wide range of applicability. This is the first law of thermodynamics. Let us start with the simplest macroscopic system, namely a certain fixed quantity of a dilute monoatomic gas. If you have watched the previous lecture on heat carefully, you will notice that there I did not specify the gas to be monoatomic. It was just a dilute gas then. Now, I introduce an additional simplification for a reason you will appreciate soon. Our dilute monoatomic gas is in a cylinder with a massless, frictionless, movable piston head with some weights placed on top of the piston head. It looks like this. The state of the system in equilibrium is given by the values of only two properties, pressure and volume. So, the state of the system is a dot on the PV diagram, which is a graph of pressure versus volume. Here is the PV diagram, and the macroscopic state of the system is just this dot here. The microscopic state of the gas depends on the position and momentum of each particle, or if we use the quantum picture, the wave function of each particle. But for a macroscopic description, just the pressure, volume, and number of particles are enough. So this dot completely represents the state of our macroscopic system. Temperature is related to pressure and volume of a dilute gas. So any two of these are enough to describe the state of a system for a fixed quantity of the gas. As you know, any dilute gas is a so-called ideal gas where the atoms or molecules are so far apart that they do not interact except when they collide. There is a property associated with any macroscopic system which is the sum of the kinetic energy and potential energy of all particles in the system. This is called the internal energy of the system and is denoted by U. For our system, U is just the kinetic energy of all the atoms of the gas since there is no other interaction energy. Moreover, since the gas is monoatomic, U is just the translational kinetic energy of all the gas molecules. Of course, we assume that during our experiments, the gravitational potential energy, other potential energies, and relativistic energy do not change. So all of these just contribute to a constant term which remains unchanged throughout. If these energies were to change during our experiments, then they have to be explicitly included in the internal energy. In our system, an ideal monoatomic gas with n particles, the internal energy U is equal to n times the average kinetic energy of each particle. So U is equal to n times m average of U squared divided by 2, which is the average kinetic energy of each particle. In the previous lecture, we have derived that for an ideal gas, the average kinetic energy of each particle is 3 by 2 kT. So for our system, U is equal to n times 3 over 2 kT. This is 3 over 2 n kT or 3 over 2 n RT. A very important point to note here and remember for the rest of our discussions and for solving problems is that the internal energy of an ideal gas depends only on the temperature. We have just justified why this is true for a monoatomic ideal gas, but this statement is true for polyatomic gases as well. The actual expression for the internal energy is not the same for a polyatomic ideal gas, and we will understand the reason for that later in the course. Using the ideal gas law, the internal energy of an ideal gas can also be written as U is equal to 3 by 2 PV. The question now is, how can the internal energy of our system be changed? The first way is by heating or cooling the gas, that is changing its temperature by supplying heat to the gas or removing heat from the gas. The second way is by changing pressure and volume in a way other than heating or cooling so that the product PV increases or decreases. This can be done by increasing or decreasing the weights on the piston so that work is done on or by the gas as this changes V. There seem to be only two options by which the internal energy of our macroscopic system can be changed. If we apply the law of conservation of energy to this system, we get what is most commonly referred to as the first law of thermodynamics. Delta U is equal to Q plus W. Here, Q is the heat absorbed by the gas, and W is the work done on the gas. It turns out that this equation is applicable not just to our simple system, but more generally to any closed system. A common type of work done in the context of physical chemistry is called pressure volume work or PV work. In our system, this manifests in the piston with weights moving up or down by delta x. That is, if a weight on this piston is removed, then the piston moves up, say to this position with a smaller weight, and it moves up by a distance delta x. The piston with the mass exerts a downward force F, so the work done is W is equal to F times delta x. The force is the pressure of the gas times the area of the piston head. So this work can be written as PA times delta x area of the piston head multiplied by delta x is just the volume change. So W is equal to P delta V. When the gas expands against external pressure, it does work at the expense of its internal energy, assuming no heat is flowing in. And so, the formula to calculate the work done is by convention W is equal to minus P external times delta V. Note that you must use this formula with the negative sign always, both for expansion and for compression. If the work done comes out to be negative, then the work is done by the gas. If it comes out to be positive, it is work done on the gas. Some of you may notice that in physics and engineering books, the first law looks a bit different. There it is often written as delta U is equal to Q minus W. Do you know why this is? I think the reason is that for engineers, the focus is on the work done by the system. Maybe an engine which runs a car, and they prefer that quantity to be positive. For chemists, our focus is on the system and its energy. So we are happy with work done on it to be positive, which increases its internal energy. The first law has three terms: delta U, Q, and W. Delta U depends only on the change in the state of the system. However, Q and W can be different depending on how exactly the state of the system was changed. Let us understand this for our simple system. The state of the system is initially this point PV on the PV diagram. Suppose further that the system is at room temperature and has diathermal walls. That is, the cylinder holding the gas is a regular metal cylinder which allows heat to flow in and out of the system freely. Now, let us remove some weights on the piston so that the downward force on the piston is half of what it was before. The piston moves up and oscillates up and down for some time, and eventually the gas attains thermodynamic equilibrium. The pressure is then half of what it was originally, and the volume is double. The expanding gas lifts the weights that were remaining on the piston and does work. The question is, what is the work done by the gas? The external pressure against which the gas expands is P by 2 and the final volume is 2V. So the work done W is equal to minus P external times delta V, that is equal to minus P by 2, 2V minus V is equal to minus PV by 2. Since the temperature does not change, delta U is equal to 0. And applying the first law of thermodynamics, Q is equal to minus W is equal to PV by 2. If we look at the PV diagram, the new state of the system is given by a point here which corresponds to half the pressure and double the initial volume. So we are somewhere here. Now let us do the expansion in two steps. Let us again start with the original state of the system PV. In the first step, we remove some weights so that after equilibrium, the pressure of the gas is 3P by 4 and the volume 4V by 3. In the second step, we remove more weights so that the final pressure is P by 2 and the volume 2V. So the final state is just like before. The question again for this two-step process is, what is the work done by the gas? On the PV diagram, this intermediate state is somewhere here. Now all these points have P times V equal to a constant which lie on this curve. PV is equal to constant. In other words, the temperature is a constant and this curve is called an isotherm. Let us calculate the work done for the two-step process. W is equal to minus P external times delta V in step 1 minus P external times delta V in step 2. So we are just going to sum up the work done in the two steps. This is equal to minus 3P by 4, 4V by 3 minus V in the first step, minus the external pressure is P by 2 in the second step, and the final volume is 2V minus the initial volume 4V by 3. And this is equal to minus 3P by 4 V by 3 minus P by 2 2V by 3, and this whole thing is equal to minus 7 PV by 12. Again, since the temperature does not change, delta U is equal to 0, and the heat absorbed is equal to the negative of the work, which is equal to 7 PV by 12. There are a few things to notice here. One, the work done and the heat absorbed are different in these two processes. These depend on the path that the system takes to go from the initial equilibrium state to the final equilibrium state. Although in both processes, the change in internal energy is the same. It is zero for both processes. The work done and the heat absorbed are different for the two processes. The internal energy depends only on the state of the system and is a state function. Work and heat, on the other hand, depend on what path was taken to go from one equilibrium state to another and are called path functions. The second point to notice is that in this case, during the expansion, the temperature of the system remains constant, and such a process is called an isothermal process. The internal energy of the dilute gas, which depends only on the temperature, remains unchanged. The gas absorbs heat from the surroundings, which is used to do work. The third point is that the work done can be indicated in the PV diagram in the following way. For the first process, let me use blue ink for this. The work done is a product of this pressure P by 2 here multiplied by the change in volume, which is this. So the work done is this shaded rectangle, P by 2 multiplied by V. In the second process, for which I will use red ink, the work done is a sum of two rectangles. The first step is this rectangle here, which has sides 3p by 4 and multiplied by this change in volume. So let me shade that. And in the second step, it is this rectangle which I shade here. You can see that the shaded area corresponds to the work done in the two processes and is just a graphical representation of the work done. You can see that the shaded area, which corresponds to the work done, is greater in the two-step process. And you can imagine that if we could do the expansion in more steps, we could get the gas to do more work. In the next lecture, we will take up this idea and discuss quasi-static, reversible, and irreversible processes. See you for that.